Welcome back to Astronomy. This is Chapter 17, Star Stuff. And in this Part 3 video, we'll look at the roles of mass and mass exchange in the life of a star. Our goals for learning: how does a star's mass determine its life story, and how are the lives of stars with close companions different? You've already seen, going back to when you learned about the Hertzsprung-Russell diagram in Chapter 15, that a star's mass determines its entire life story because it determines its core temperature. So think back to the Hertzsprung-Russell diagram. We take a star that starts out with a high mass, let's say right about here at about 20 solar masses. That's an extremely large star. And its lifetime on the main sequence will be relatively short, only 10 to the 7th years, or about 10 million years. Because of its higher core temperature, it burns through the fuel much more quickly than a lower mass star. It's got not only the proton-proton chain, but also the CNO cycle, so it'll burn through the fuel more quickly. If you take a lower mass star, something like our sun, at about 1 solar mass, it doesn't have as much mass gravitationally crushing down on the core. The core temperature isn't going to be as high. And so even though it has less mass, less fuel to burn, it burns through it at a much lower rate. So let's take, for example, let's go back up here to the 20 solar mass star that has a luminosity of about, look here on the vertical axis, 10 to the 5th solar luminosities. So even though it's got 20 times the fuel that the sun does, it burns it at a rate 100,000 times more quickly. That's why it dies more quickly. And here's the sun, given its mass, which determines its core temperature. That determines the rate that it's going to burn through its fuel. It'll last for about 10 to the 10th or 100 billion years. And then we come down here to a star of 0.1 solar masses. Now, that implies that it's only got about 1/10 of the hydrogen in the core that the sun does, 1/10 of the fuel tank. But look where it is on the luminosity scale, between 10 to the -2, maybe 10 to the -3. So it burns the fuel at a much slower rate. So those things can live as much as maybe 1 trillion years, 10 to the 12th years. High mass stars with greater than 8 solar masses, so right about here and up, have short lives, eventually becoming hot enough to make iron and end in supernova explosions. And I'll add to that, in ways that you'll see more in Chapter 18, they will end as either a neutron star or a black hole. Low mass stars, less than 2 solar masses, so right about here and down, have long lives, never becoming hot enough to fuse the carbon nuclei in the core, so they end up as white dwarfs. And then intermediate mass stars, which are between 2 solar masses and 8 solar masses, so right about in here, can make elements heavier than carbon, such as oxygen and neon, and they still end up as white dwarfs, just like low mass stars do. So all of this has been basically a review of what you've seen previously in Chapter 17. And I also want to take this time to remind you that when we talk about low mass stars, we're looking at all these reds, oranges, yellows, and on into the whites. We're looking at 96% of stars are low mass stars. They will end up as white dwarfs. And only a small percentage, very small percentage, are intermediate or high mass stars, and particularly high mass stars. You're looking at about 0.4%, which end up as neutron stars, and a very smaller minority will end up as black holes. Study this chart here. Learn it well, because it very briefly and concisely gives you the life cycle of stars. So we start with a star as a stellar nebula, or a protostellar nebula actually, because it hasn't yet become a star, and its life track will go one of two ways. This chart here says average star versus massive star. Let's be more precise about that. I would say this is at the top. Let's call that a low or intermediate mass star. And down below, that's going to be a high mass star. Well, let's follow the life tracks. Let's go for low or intermediate mass star, which again is going to be by far the majority of stars. It grows to become a giant star. And eventually the outer layers float away and it becomes a planetary nebula. What's left, as the planetary nebula eventually cools off and isn't bright anymore, what's left is just the white dwarf that's left behind. For a high mass star, let's follow the life track on the bottom. A star, it's going to be a blue star. It will grow after it leaves the main sequence into a supergiant. And when it gets to the end of its life, when the core has become iron, it will explode. Remember, that's where the core has shut down, no more nuclear fusion. The entire star collapses. The outer layers of the star will rebound off of the core, and that is the supernova explosion, all that material going outward. The core itself will crush down into a ball of neutrons. And so there it is, a neutron star, and we'll talk more about those in chapter 18. If it is a very, very high mass star, then not even the neutron degeneracy pressure can hold up against gravity, and it'll crush down to an infinitesimally small point, and that's called a black hole. So learn this chart well. These three objects that are left over, either a white dwarf, a neutron star, or a black hole, those are the objects that we will look at more intently in chapter 18, the bizarre stellar graveyard. Here's a mystery that astronomers came upon in the 20th century. There was a star, a binary star called Beta Persei, otherwise known as Algol. And so there are two stars that are in orbit around each other. Presumably, they were formed at about the same time. And this binary star consists of a 3.7 solar mass main sequence star, such as you see down to the left, a blue star, fairly large blue star, and a 0.8 solar mass subgiant star, so the larger red star, red giant, actually a subgiant. What is strange about this pairing, and how did it come about? Well, what's strange about the pairing is you think that if they formed at the same time, and if you have two stars that are close companions to each other, you can assume that they were formed in the same cloud. Then you think about the blue main sequence star, about 3 solar masses, so it's right here. And then you think about the 0.8 solar mass subgiant, so it's going to be up here somewhere. Now, the weird thing is that subgiant, where did it come from? Well, it was originally a giant or a main sequence star of about 0.8 solar masses. So it was about maybe right here when it was on the main sequence. So we have the blue star that formed right here at about 3 solar masses, and the reddish orange star that formed about here. Now, the weird thing is that the red star on the main sequence would have had a longer lifetime. It would be on the main sequence longer than the blue star because the red stars, the orange stars, last longer than blue stars. So the question is, how has it become a subgiant already? How has it gone through its lifetime already before the blue star quit being a main sequence, and it's already gone up to the subgiant phase? So that was the mystery. And then astronomers figured out what was going on. The stars in Beta Persei are close enough that matter can flow from the subgiant onto the main sequence star. So here is how they began. You look at these paintings here. We have to the left a main sequence blue star and to the right a red star. And again, this star known as Beta Persei, otherwise known as Algol. So in the first picture, Algol, shortly after its birth, the higher mass star on the left evolved more quickly than its lower mass companion on the right. And that's what we know high mass stars do. They evolve more quickly. All right, so then let's go down to the second picture. The higher mass star on the left, it grew to become a giant. And let's read the caption here. When the more massive star expanded into a red giant, it began to lose some of its mass to its normal hydrogen core fusion companion. And so this is the idea of mass exchange. The more massive star on the left that's grown to become a giant, it has grown so large that its outer layers are more gravitationally attracted to the other star than they are to the star that they belong to. So those outer layers start to move on over to the star to the right. You notice what's happening to the star on the right. In the painting, it started out as a red star. Now it's a more massive yellow star. So it's going to keep on attracting the mass. Let's go down to the third picture. Algol today. As a result of the mass transfer, the red giant has shrunk to a subgiant, and the normal star on the right is now the more massive of the two stars. So this is as we see it today. On the left is the 0.8 solar mass subgiant, which actually now we see it was originally a white or a blue star. It grew to a giant, but then it shrunk down to a subgiant. And the blue star that we see of about 3 solar masses, it actually started out as a low mass red star, but then grew because it gathered more of that material from the star on the left. So mystery solved. And this is the kind of thing that we can expect to happen when stars are close companions to each other, when they are in tight orbits around each other. And so we see this when we have globular clusters, particularly towards the center of globular clusters. There are a lot of stars of different masses, so different spectral types, and towards the center of a globular cluster, they're pretty tight near each other, so we can expect to see a lot of that mass exchange. What have we learned? How does a star's mass determine its life story? And this has really been a review of concepts you've been learning since chapter 15, when we started to put together the Hertzsprung-Russell diagram. Mass determines how high a star's core temperature can rise, and therefore determines how quickly a star uses its fuel and what kinds of elements it can make. How are the lives of stars with close companions different? Stars with close companions can exchange mass, altering the usual life stories of stars. And the star Beta Persei, the double star, otherwise known as Algol, is a great example of that. That's the end of chapter 17. Have a great day.